Hi, everyone. Welcome to Foresight's Molecular Machines Group. Really excited to have so many of you here, especially excited to have Emanuele here. Emanuele actually won our Distinguished Student Award a few years back, and now he's back to tell us a little bit about probing supramolecular interactions in molecular machinery with numerical simulations. Quite a mouthful of a title, but really excited for your presentation. I'll be monitoring the chat. I'll share a little bit more info about you in the chat. But for now, the stage is yours. Thanks a lot for joining.
Okay, thank you, Alison, for your nice introduction. Can you hear me loud and clear and see the slide?
Yep.
Okay. I want to thank the Foresight Institute to having me, and let me go on thanking people first, because my work wouldn't be possible without all of them. Today, I will mostly focus on the result that I obtained at Northwestern with my colleagues in the Gingrich group, but I will present them in the context of my previous work with people, well, mostly formerly in the group of Professor at the University of Manchester, and also their collaborators and people that inspire me through several discussions. And I like to notice that many people here are or have been fellows of the Foresight Institute, and we even got to a Feynman Prize. Feynman Prize is for theory. So today, I will talk mostly about molecular rats, and I guess that most of you know about them. And anyway, my talk should be self-contained. However, for those of you who are interested in learning more about molecular rats, let me point you to these two recent and quite complementary reviews. One from the group of Giulio Ragazzon, which I also contributed, and one from Stefan Dave and Ben. And taking inspiration from American pop culture, the challenge is to read both of them in the same day. And if you do it, be sure that you will become an expert in molecular assets. So today I want to talk about a specific topic in this literature, let's say, that is the topic of power strokes, and in particular, the fact that we can look at synthetic molecular motors as a proxy to understand biological motors. Let me start. Example of kinesin. So kinesin is a biological motor that probably we all know is a protein that can literally walk along this structure called microtubules that are found in our cell. And this is an autonomous and catalysis-driven ratchet. The kinesin can achieve its directed motion because it is coupled through catalysis to the ATP to ADP decomposition. And I want you to focus on this high level and simplified representation of kinesin stride, and in particular on this step here. So this is the step that has to do with the power stroke, and is the step that is actually performing the movement in space through a large amplitude conformational change in which the leg of the kinesin is lagging behind in this conformation passes ahead of the other. And what's special about power stroke, let's say, is that very often in biology, these large amplitudes of motion are energetically downhill in the direction of motion, meaning that the conformation, the pre-power stroke conformation with the leg behind, let's say, is energetically higher than the post-power stroke conformation with the leg ahead. In the language of chemistry, you can think about this as a reaction whose equilibrium constant is higher than 1. And this is what in the literature is typically called a power stroke. So this free energy downhill character. And since they are so typical in biological motors, many work basically look at power strokes as the origin of directionality. And let me specify now that these double inverted commas here are not like a typo. Is to stress that power stroke as a terminology is not necessarily the best terminology, because it's a very macroscopic terminology applied to the nanoscopic world. But for convenience, I will use this terminology because it's very common in the literature. But just think about power stroke as it is basically larger than 1 equilibrium constant. And so the idea that power strokes can predict the directionality of molecular motors is the basis of the so-called power stroke mechanism. There were many papers describing this mechanism. My favorite definition is this one. It says that in many ways, the power stroke mechanism is the molecular analog of an inclined plane. And you can see this macroscopic like intuition applied to the nanoscopic work. And so because of this inclined plane scenario, the power stroke mechanism tells us that if we have an equilibrium constant that is larger than 1, we expect the directionality to be forward. If we have an equilibrium constant smaller than 1, the directionality will be backward. And in particular, if we don't have a power stroke, so if our conformational states are degenerate, we do not have directionality. There were many experiments claiming actually to that I call power stroke engineering in this slide, claiming that by acting on the power stroke, people could basically change the directionality of a biological motor, even inverting this directionality. And actually, there are other contexts, for example, light-driven systems and energy assets, where power strokes actually control the directionality of the motor. But today, I won't talk about light-driven and system and energy assets because I want to focus on catalysis-driven autonomous molecular motors. By reading this literature about biological molecular motor, one has the impression that the power stroke mechanism is quite solid. However, in the last decade or so, a theory was developed showing that catalysis motors are actually best described as what are called Brownian assets, Brownian information assets. In particular, this idea of the Brownian asset mechanism, in which the power stroke is irrelevant for determining the directionality and other properties of motors. Instead, what controls directionality in the Brownian asset mechanism is a property called decay symmetry that has to do with the ability of different ability of different conformation of a motor to catalyze the chemical reaction that is driving the motor. So in case of kinesin, this would be that different conformation of the kinesin have different releases rate for the ATP to ATP conversion. And in this picture, actually, changing the power stroke is irrelevant for the directionality. So we have something like this flat line. Of course, we are at the Foresight Institute, so we like Steinman's manifesto that what I cannot read, I don't understand. And synthetic chemists took this very seriously in the last years. So, for example, here we have a beautiful example of a synthetic catalysis-driven molecular motor. So this is a small motor that works in the same way as biological motors because it's driven by the catalysis of some fuel into some waste. And it achieves like the unidirectional motion of one part of the molecule with respect to the other. And what is important is that in this system, if we look at the analog of the power stroke in biology, so if we look at these steps that are the steps realizing this directional motion, the conformations involved in these steps are actually degenerate. So the equilibrium constant for these steps is 1. So we don't have a power stroke in this molecule, in this motor, but yet we get a non-null direction as predicted by this Brownian information asset picture. Of course, one swallow does not make a summer, so we need other example. This one is the first ever synthesized autonomous chemically driven molecular motor. And again, if we look at the network of reaction representing this motor and we look at the steps implementing these large amplitude conformational changes in the motion in space of the motor, again, we have that we don't have power, and yet we get the directional motion. We also have recently published this other set of experiments where the group took basically a rotaxane that is chemically driven. They changed the binding site on one side of the rotaxane so that they could basically change power stroke, so the stability of the conformation with the macrocycle on the left and on the right, and yet they could see that in all these cases, the directionality is not altered by the introduction of these energy differences. So if you want to know more about the power stroke and the information Brownian Ratchet mechanism in the context of molecular motor, I point you towards this perspective that we published 2 years ago. But today, I just want to summarize what I have told you with this slide. So on one side, we have the power stroke mechanism that is still quite popular among biophysicists. The reason of its popularity, in my opinion, is it is a very powerful idea. The fact that you can explain the directionality of a very complex system, such as a protein molecular motor, by only looking at 2 states. So this is very appealing to rationalize those complex experiments. It has been guiding successful engineering experiment of biological motor. As I was mentioning before, there are many papers claiming that one can change the directionality of a motor by acting on the power stroke, but this is wrong to the best of our current knowledge, because molecular motors are actually just described as information ratchet. The information ratchet mechanism is sound and is based on Peirce principles. In particular, you can use as need mass action kinetics and microscopic reversibility to basically build a model, the Brownian information ratchet mechanism. It has been experimentally tested, as I've shown, but doesn't explain why power stroke are common in biology and the successful power stroke engineering. This is the question I want to focus on in the rest of my talk. And there are many ways to answer this question. So why power stroke intuition seems to work in biophysics and why power strokes are frequently observed in nature. So our first answer is that this is a mass hallucination and we should not care about biophysics literature. But of course, this is very hard to give. An alternative is that biological and synthetic motors are fundamentally different. Again, these are to give because to the best of our knowledge, the same fundamental principles of physics and chemistry apply to both biological and synthetic molecular machines. So at least, or we'd like this to be true. And another possibility is that power strokes are useful to control and optimize something different than directionality. So they are present in nature not because they optimize the direction, they control directionality, but because they optimize something else. And this is actually probably true. We had some paper in the past showing that the change in the powers can change the efficiency with which molecular motor use the free energy from the driving, and or power stroke can tune the speed and the information and energy storage capability of a motor. But I won't talk about this result today because, these ideas can explain why power stroke are present in nature, but still they cannot explain why power stroke intuition sometimes seems to work in biophysics experiment, or at least is claimed to work. So I will focus on this third possible answer, that there are effects that kinetic models have overlooked or did not explore enough. So this will be my focus today. And of course, to explore this last hypothesis, I cannot rely on kinetic models because is the thing I want to go beyond. And also I cannot rely on experiment because I'm not an experimentalist myself, and still doing systematic experiments on these on these systems is still quite difficult. So I will adopt a slightly different version of Feynman's manifesto, that what I cannot simulate, I do not understand. So this will be my approach in the following part of the talk. And the idea is basically to come up with a computational model of a catalysis-driven motor that allows to explore the fundamental features of catalysis-driven motors in silico. So in other words, a model that I can simulate in a computer and that is built out of the very minimal physical ingredients dominating the physics, the nanoscale. Let's try to see how this model works. So this will be my most complicated slides. Try to stay with me for a few minutes because I'm going to tell you what are the ingredients of my computational model. So the ingredients are actually very simple. So just a set of spheres that can move in space with Brownian motion. We can do this by implementing these equations that are called Langevin equation. There's no need that you understand the details of this equation. You can just think of them as like a stochastic version of Newton's equation, where is skilled and we have a noise that is producing the Brownian motion. And if the noise has certain properties, if the noise respects this equation, we are guaranteed that the dynamics is macroscopically reversible. So if you want these conditions on the noise are the analog of microscopic reversibility in a chemical reaction net. But basically the message is that I just want some spherical particle moving around with Brownian motion. Then I want these particles to be able to experience some soft interaction, where I can tune how much this particle attract each other and how much this particle attract each other and how much this particle revert each other at short distance. And the last ingredient is that I want to be able to bound two or more particles with some strong spring-like interaction such that I can define some sort of geometry. Okay, so these were the ingredients, and now I want to show you how we can build a driven motor out of only these ingredients. And to show this to you, I prepare some movies. So basically, this is just a movie in which I just pick like some black spherical particles and I glue them with this spring-like interaction such that I can make a ring. And then I prepare another ring that I interlock with the first ring of the particle. And what is basically what you expect. When you evolve this system with Brownian motion, basically that this catenane just wiggle around and the small green ring just goes around randomly. We can add some binding site to this catenane. So these orange binding sites that you see now are basically attracting the green ring with some of the soft interaction I was talking about. And you can see visually that the dynamics basically slows down. So instead of the green ring wandering around in random position, now you have that most of the time the green ring is at the two binding sites, as you would expect from this kind of simulation. So if we take the last video that I've shown you, so the video with the two binding sides, and we compute how many times, we count basically in the simulation how many times the green ring performs a clockwise cycles and how many times it performs a counterclockwise cycles, of course, we see that there is no preference because our dynamics is microscopically reversible. We have no energy input, and so we cannot make a motor out of this simple system. In order to make a motor, in particular catalysis-driven motor, we need to couple this system with some sort of chemistry. So now I will try to explain you the crucial idea of this kind of simulation, that is how we can simulate a chemical reaction, or at least something that looks like a chemical reaction with this simple ingredient. So the idea is the following. So let's take 4 blue spheres, for example, in this configuration, and let's attach these blue spheres with some springs so that the blue spheres wants to stay very close to minimize the energy and the tension of these springs. But then we can initialize this cluster of spheres with a red sphere inside. So the effect of this red sphere is, of course, to stretch a little bit these springs, such that now this cluster is a metastable species, because genetically best preferred configuration is the configuration where the red particle escapes, so is outside from the cluster, because we can minimize this spring energy. But in order for the red particle to escape, we need some quite large thermal fluctuation, making this for the red particle to escape. So if you tune your parameter, you obtain basically that this species is metastable and it will never basically react. So you will never observe the escaping of the red particle during the dynamics. So if you want, this is a chemical reaction that is very slow, is thermodynamically favored, but is slow. So you can try to design a catalyst to help this reaction to happen. And with our simple ingredient, we can design a catalyst in the following way. So we can think of taking, let's say, 3 spheres, these white spheres, and tuning their attraction such that the 2 lateral spheres can attract the blue particles such that they stretch them when the cluster, the FTC cluster, is closed. And we can also add the feature that the central sphere attracts with this soft interaction, the red sphere in the middle. If we simulate this system, so if we just simulate, if we evolve the dynamics of this this cluster of spheres plus this catalytic unit, what we observe is continuous version of the Michaelis-Menten field, because this interaction will basically make will make the cluster getting close to the catalytic unit. The interaction will help stretching the blue particles such that the red sphere can escape, but due to this attraction with the central sphere, the red sphere can stick around on the central white particle for a bit before it leaves. So overall, we have this catalytic mechanism for helping the composition of this FTC cluster into this ETC and C particle. So we literally have a way to simulate a catalyzed chemical reaction within our fully classical molecular dynamics simulation. And what we can do is to insert these catalytic units into our concatenate. And now we have something that looks more like the 2016 catenary motor from the Lee group. So for example, if the motor happens to be in this conformation, one catalyzed reaction can touch this barrier here, and this barrier can eventually leave. And we actually have something that we can call kinetic asymmetry, because when the green ring is here, so it's on this binding side, it hinders a little bit this catalytic side, so that it is more difficult for the fuel to get close here and to touch this barrier than when the ring is on the other binding side. So we have implement this. So we have automatically this effect that different motor conformation can catalyze the fuel to waste decomposition at different rates. So we do have kinetic asymmetry. Then, of course, if you want to simulate this system, this motor for long times, we need a way to keep a chemical potential gradient. So we need a way to keep the concentration of FTC species high and the concentration of ETC and red C particles low. And we can do that in our simulation with technically it's a Monte Carlo procedure, but practically what we do is injecting some FTC in the simulation box and extracting some C and ATC species from the simulation box in a way that is thermodynamically consistent and keeps a fixed chemical potential difference between these two species. I had prepared other movies to show this more explicitly, but I think I will keep these movies and maybe we can have a look to them at the end. So I will directly jump here. So if we now simulate this system as we did before, but now with the full motor, with the two catalytic units, and with this injection and extraction mechanism of the fuel species, and we count the clockwise and counterclockwise cycle, we do see that this system is a motor and reproduces the fundamental features of the Brownian information ratchet mechanism, in the sense that now, because of this configuration that I choose, clockwise cycles are more frequent than counterclockwise cycles. So I have a net directionality in my motor. So if you want more details on this setup and you want to see like more different kind of results, you can look at this publication from the English group 2 years ago. Now I want to tell you how we can use this machinery to invest systematically the effect of power strokes, because now we have full control on the energetics of our system because of this soft interaction I was talking about. If we, for example, make the red particle more repulsive with respect to the green particles, we have that now this conformation when the ring is proximal to this barrier is higher in free energy. And then likewise, if we add some attraction, so if we now make the red particle attractive for the green ring and vice versa, the green ring attractive for the red particle, because these interactions are always reciprocal in this model, we can basically make this conformation now lower in free energy with respect to the other. So we can play with this power stroke, or if you prefer, with this equilibrium constant and see what happens. At any moment, we can, so for any simulation parameter, we can quantify the equilibrium constant in many ways. One of them is basically to extract from the simulation the forward, the clockwise rate and the counterclockwise rate. And because of detail balance at equilibrium, you have this ratio is the equilibrium constant. We can quantify the directionality, for example, in this way, with this quantity that I will call bias, that is just the number of clockwise cycles divided the sum of all the cycles. And for example, one first experiment that we can do is to fix the repulsion at some high value, so 3 different values of the repulsion, and varying the equilibrium constant by only varying the attraction between the green ring and the red sphere. So with this, we can basically tune the equilibrium constant to be larger than 1 or to be smaller than 1. And these are the results. Another experiment that we can do is to do the opposite, is to fix some value of the attraction and change the repulsion, in this case, within a larger range than before. And we see this kind of results. If you remember the plot that I showed you before, this one, so both these set of simulation results are somewhat different from what you would expect from either the power stroke mechanism or the simple information Brown information budget mechanism. And the first thing that is evident from this plot is that the power stroke is actually not at all predictive of the motor directionality. Because, for example, here the equilibrium constant is larger than 1 and we have forward directionality, but here the equilibrium constant is smaller than 1 and we still have forward directionality. And when the equilibrium constant is 1, we still have directionality. Here we even have a case in which the equilibrium constant is larger than 1, but we have negative counterclockwise directionality. Actually, the only data point that follows, let's say, the prediction of the power stroke mechanism is this one. But basically, this data show clearly that the power stroke mechanism does not hold for this system. And so one first conclusion is that the simulation can be seen as an independent and first principle confirmation of kinetic model results, such that those of Professor Asturi. And then, of course, basically anything can happen, as I was describing. So, for example, I don't want to, so we can rationalize each of these data points and explain them according to the physics of the model, but I don't want to focus on too many system-specific features. Just if you're wondering why here the directionality drops and even goes negative, is that at some point the repulsion is so small that the ring can start leaping over the barrier. So of course this decreases the bias a lot, and it can even cause the directionality to go negative. But overall, the second take-home message that I want to highlight is that power stroke can impact the directionality in a manner that is in apparent conflict with a kinetic model suggestion of irrelevance, in the sense that we don't have a straight line as we would expect from like a simple application of kinetic models. And I want to take a bit of time to explain why it is so. The typical way in which directionality is quantified according to kinetic model is something like that. We have the chemical structure. So we have our motor. We can do experiment to extract the kinetic rate constant, and then we can compute the bias in the kinetic bias in different ways. We have expression like this one telling us how many clockwise cycles I have over counterclockwise cycle. And this expression is an expression where only the rate constant of the chemical reaction appears. So we don't have the equilibrium constant appearing in this expression. So if you want to use a kinetic model to predict what happens when you change the power source, so when you change the equilibrium constant, the simplest thing to do is say, okay, I change the equilibrium constant in a way that is thermodynamically consistent. In the kinetic model, I can do that in isolation with respect to all the other rates, and so my directionality does not change. This is actually in agreement with experiments like this, for example, where the thing that we change experimentally in order to change the equilibrium constant is this station that is far away from the catalytic site. So it's very plausible that these structural changes affecting the equilibrium constant does not affect the chemistry at the level of this catalytic site. But instead, if you want to do the same in a different system, so let's for example, in this catenary motor, in this case, one way to change the equilibrium constant such that we introduce a power stroke in the system is, for example, very similar to what we do in the simulation. So adding some kind of attraction between the ring and the barrier such that now the proximal configuration is more stable than this configuration. In this case, it's not hard to imagine that such change can also affect some rate. So for example, if the ring attracts the barrier, it's possible that this attraction not only stabilizes the state, but also makes the barrier removal reaction more difficult. So we have a structural change that is meant to change the power stroke, but can act in not trivial ways on all the possible rate constant. And it is difficult to come up with a theory that tells us how such a structural change affects all the kinetic rates of our model. Our simulation basically do not have this problem because we go directly from the simulation to the bias. So somehow it's like doing the real experiment and see what happens without passing through a kinetic model. So all this complexity that I was describing is encoded in our simulation. And indeed, we can observe that when attraction between the red particle and the green ring is high, not only this introduces a power stroke, but it also slows down the barrier detachment reaction. And that, and this is basically the reason why with this simulation, we could catch all these side effects that typically are overlooked by kinetic model. Then another point that I want to make here, now this in favor of kinetic models, is that, of course, these simulations are qualitative, they are good if we want to investigate these fundamental effects that might emerge in Brown information rasets, but because they are so simple, they cannot provide us with quantitative predictions and characterization of experiments. While kinetic models that are directly informed by experimental data are very good to actually quantify what is actually happening in an experiment. So all of this to say that yes, we have some differences between our simulation data and what we could naively expect from a kinetic model, but our data are not in conflict with the Brown information raset mechanism. They simply show us that there might be some side effects that are not easy to grasp by using kinetic models. And if you are familiar with the literature, and some of you definitely are, in my opinion, these simulation data are a concrete and direct demonstration of the effects anticipated in this perspective that we published 2 years ago. So just to say the same thing with different words, then if someone does an experiment and does not observe this straight line, it doesn't mean that the system does not follow the Brownian-Racet mechanism. It simply means that somehow the structural modifications are introduced in the system to change the equilibrium constant, also affect other features, in particular features about catalysis in these non-trivial ways. And my last point is basically the following. So if we look at this data, we see that there are regions in which there is a positive correlation between the power stroke magnitude and the directionality. So here, if I increase my equilibrium constant, I get more directionality also here. And by the way, in our simulation, these regions happen to follow exactly in the region where the motor is also fast. So these are plots of the current of the motor, but this is again a system specific feature. My point here is it's not impossible even if Brownian-Racet mechanism that have some region in which there is a correlation between the power stroke magnitude and the directionality. And this, in my opinion, is a possible explanation of why the power stroke intuition, although incorrect, because we saw that the Brownian power stroke mechanism does not apply to such systems, can sometimes give the impression of working well and can therefore be used as an effective engineering tool. So my point here is that it might be that a motor, either biological or synthetic, happens to fall in a region where you do have these positive correlations. And if this is so, it means that the power stroke can be a knob to change in order to optimize the directionality. Of course, this is not ideal because to optimize directionality, one would like to act directly on catalysis, for example, on addition state energies. But since that is very difficult to do, the power stroke in this condition can be a good proxy and a parameter to optimize in experiment. So again, this, in my opinion, is a possible explanation of why power stroke engineering seems to work in biophysics. And with this, I jump to the conclusion that are this one. So in the Gingrich group, we built a platform to perform in silico experiments probing the output of a catalysis motor. And in my opinion, these simulations are very nice because there are no other cases in which one can directly and explicitly simulate catalysis within molecular simulations. And I point you to the original reference if you want to know more about this. Even if our model system is super simple compared to the complexity of synthetic or biological motors, we have non-trivial behaviors that demonstrate nuances of the Brownian information-Racet mechanism that go beyond what can be expected with kinetic models. And a possibly relevant conclusion for the design of molecular machines is that power stroke should or can be considered as a design features in catalysis-driven molecular motors, offer also an interpretation for biological. And a discussion of these possible effects was already presented in this perspective. But now with this simulation, we could basically demonstrate it explicitly within a molecular dynamics model. And if you want to know more and also see more videos, there is a preprint on KMR5 that was out yesterday with the title of this presentation. And since at the end of this kind of presentation, the Foresight Institute always asks us to come up with some challenges for the future. Here are my challenges. The one that is more related to my talk is that it would be nice to develop other general and predictive computational models to simulate out-of-room requirement machine learning explicitly. And this is because the simulation that I shown you today are very specific for the catenate motor, and it's very difficult to apply the same to build models for other motors with the same simple ingredients. So it will be good to have a strategy to systematically build this kind of simulation for different systems. A challenge that is more relevant for the field in general is finding applications of out-of-equilibrium requirement machinery and scaling their functioning up to the macroscopic world. I think this challenge was basically pointed out in all the presentations about synthetic molecular machines in this seminar series. And the last but not least is that I would like to see more dialogue between the artificial molecular machine and biophysical communities, addressing the challenge of finding a common language and vision, because I really think that those communities can benefit from talking to each other more. With this, I finish. Thank you for your attention, and sorry again for the inconveniences with the that were not predicted.
It was really worth it. Thank you so much for presenting. That was quite a lot of content to digest. And I especially love that you actually addressed the future challenges on a final slide. This is awesome. So we have more time for a few of the other questions here in the room. We have one from Paolo and one from Dean. Maybe Dean, do you want to kick us off with your question? And then Paolo, you can maybe go after.
Yes, I disagree with the assertion that power strokes seem to work in biology. From my perspective, they simply don't. The data, much of the last 50 years has been people getting real good data on molecular machines that shows that the power stroke doesn't work, and then going to extraordinary lengths to attempt to suggest why it might. For example, the Carter and Cross experiment, in which you push on a kinesin and it moves backwards. And the natural thought with a power stroke model would be then it must be synthesizing ATP. And so if we add extra ATP, it'll slow down. In fact, when you add extra ATP, it speeds up in the backward direction. And that is consistent only with a Brownian ratchet mechanism and not with a power stroke. And yet they had a news and views on that paper instead of acknowledging the obvious that it is in fact consistent with a Brownian ratchet. They analogized kinesin with a toy steam engine. And I think I used at one ACS meeting the observation that it's about as likely to understand the motion of kinesin on microtubule in the context of a toy steam engine as it is to understand the apparent motion of the stars in the constellation Ursa Major by studying the biology of bears.
So, yeah, I perfectly agree with you. And I'm not saying that with this work, I want to demonstrate something that we didn't know before. And if you read the reviews that we have written or your works, clear that the power stroke mechanism doesn't work. But I think that what you just said is the demonstration that still this idea of interpreting biological motor with power strokes mechanism persists in the literature. So I think it's very useful and positive to show the nuances in other
but
systems.
It's not based on experiment.
Yeah, but still, if you talk with some I'm not saying all biophysicists, but if you talk to some biophysicists, they still put this power stroke idea in the title. And if you want, so if tomorrow someone comes up with some data that actually align with the power stroke mission, I think that now we are prepared to say, okay, so this is not an experimental demonstration that the power stroke mechanism work, because this kind of behavior is perfectly accounted for by the Brownian information mechanism. through these side effects I was trying to explain.
All right. All good, Dean? Great. We have a question from Paolo, who is trying to be joined right now at this moment, but it's a little bit further up there. It's rather technical, but Emanuele, if you want to answer it, it's under...
Okay, so I need to read the chat then. Okay.
Or I can repeat it.
Oh, you're here.
It would be great.
Repeat it.
Yeah, no, thank you very much for the talk. It was very nice and inspiring. Actually, I'm not in this biomolecular motor community, and I would like to rewatch the video recording tomorrow. First a comment, I'm not sure. I really like the idea to try to model a complex system with a toy model in this simple soft sphere model. I'm not 100% sure that this can capture all the physics that it's in real system. To live with that. And then in your graph, I didn't really get, because you were always showing that the equilibrium constant is a function of these two epsilon, while you have also the fuel that it's tetrahedral snapping out the intruder there, and this depends on the spring constant that you have there.
So thank you for your nice comments. If you want to read more and get technical, there is like the chemical vows with also the supplementary information where you definitely find the technical answers on the fact that the model doesn't catch all the physics. Yes, and this was basically the point I was trying to make when I spoke about the quantitative versus qualitative usefulness of kinetic models and simulations. So I completely agree. Actually, our model doesn't even know that it is a molecule. You have the Langevin equation with their parameters can be colloidal parts or can be molecules. But so there is also no notion of scale. Of course, it cannot capture the complexity of chemistry. And on the last point, the equilibrium constant I was talking about is only the equilibrium constant between the and the proximal conformations, basically equilibrium constant of the shuttling process, where nothing changes except the position of the green ring. So in that case, that equilibrium constant does not depend on the fuel parameters because there is no chemical action involved in that process. So you can, so the only difference is basically the position of the ring. So the only relevant energy that is changing is the interaction between the barrier and the green ring and by those attraction repulsion parameters.
If I can reply quickly, I'm totally fine with this coarse grain approach. It goes in this Martini force field direction where you have spheres with groups of atoms. Still, when you are talking about atom-atom interaction, you have something that goes beyond the radial symmetry. You have directionality of orbitals, and this cannot be captured. But it was very interesting to see this modified version of Lennard-Jones. We are going in a similar direction, so maybe I will contact you for some discussion.
Okay, it would be great. Yeah. There are some nuances of between that you will find in the supplementary information, but like to discuss.
Thank you very much.
Okay. Awesome. We're 1 minute over time, but thank you so much for joining. That was a really wonderful presentation. Thanks everyone for your amazing questions. We'll be publishing the video in about a week or something, but thanks a lot, Emanuele, for joining. Have a good one.